now we will just prove the laws of reflection on the basis of your wave theory. Now how we are going to prove it? So let's say, for example, so this is the incident wavefront which I have shown, A1 B1 or A2 B2, that is bounded by your those two wave normals. Then again it is going to strike at the interface your xy. Then the A1 or that A2 will reach at the interface first, then definitely it changes its direction, but at the same time this B1 which is over here, now the waves from B1 will just travel in the same direction, and the waves which has been transmitted from A1 just had changed its direction. So what we will do, the time the wave from B1 will reaches to point C, the wave from A1 will travel some distance. Yeah, so definitely how much distance it will travel, the same distance that has been traveled by that wave from B1 to C. That's it. Yeah, so you have to do just you can do one thing. So definitely of same radius, that B1C, by considering the center at A1, you have to just draw this semicircle. Yeah, so if you draw this semicircle, so the wave that reaches at C, and if you just draw the tangent over here, so this CD, the CD is nothing but the reflected wavefront. So this CD, you can say that that is a reflected wavefront. Yeah, and that A2 B2 or A1 B1, already I just told you that. Yeah, so that is your incident wavefront. So this is your incident wavefront. Now next, what you can prove that, so according to that, your angle, that is I, has to be equals to angle R. Fine. So this is also you can just prove over here for this particular case also. Yeah, fine. So now when I'm saying that for these two triangles, so if you observe this two triangles carefully, so let's say I'm just saying that this angle of reflection over here, so this angle of reflection for this particular case, that is again, that is angle of reflection R, then this has to be 90 minus R, then this has to be R. Yeah, so this has to be R. So this angle which I have shown over here is nothing but R. So if you just consider this triangle, let's say that is a A1 B1C and triangle your A1 BC. Yeah, so in this A1C is common. Yeah, again A1 B1 is same as that of here, obviously that is a CD. At the same time, that angle B1 and angle D, they are also 90 degree. Yeah, so they are also 90 degree. So you can say that these two triangles are congruent. These two triangles, definitely we can say that congruent. Again this is I, then further you can say that this is 90 minus I. Further you can say that this A1, yes, so this A1, again I can say that it is nothing but I. Yeah, so definitely this A1, again we can say that it is nothing but I, and this is nothing but what we can say R. So these two triangles are congruent triangles. So definitely this angle I is same as that of your angle R, and that what you have to prove over here, that is the law of reflection on the basis of your wave theory, which we just proved that angle I is same as that of your angle R over here. Similarly, yeah, the same thing which I just shown, that is the incoming light of path, then mirror, it will get reflected. Similarly, the same result that we have got it. So now you have to again prove the refraction of a plane wavefront at a plane surface. So this A1 B1 is the incident wavefront. Again we can say that, so when the wave reaches at point A, according to Huygens wave theory, it will act as a secondary source of light, emitting the light in the second medium whose refractive index is different, obviously. Yeah, so its velocity is different in the second medium, but by the same time the wave which is at B1, it is still in the same medium. Yeah, so definitely now they are just traveling with the different speed. So when this one entered into the second one, but definitely that from B to C. Yeah, so still it is traveling in the first medium itself. Yeah, so what we will do over here, the time by which the B1 will reaches to the point C, in the same time the second wave from A will reach up to the point D. Yeah, so what we can do over here, so this is I, 90 minus I, this is I, and this is also R. So what we can write it down for this particular case over here, obviously that's sine I. So this sine I, how we can write it down? Yeah, so this sine I, again, that we can say that is the opposite side. So which is, let's say, I will say that there is a B1C upon hypotenuse, which is the AC. Similarly for your sine R, so sine R, what you can write it down, that is the opposite side. Yeah, that is the AD. Yeah, and again similar to that, what we can say for this one, so which is nothing but your AC. Okay, so this, just take the ratio, that is a sine I upon sine R. So this B1C upon AC, and this is AC upon AD. AC get cancelled. This is B1C upon AD. Now what is the B1C? That is a distance. Yeah, so velocity is equals to distance upon time. So this one, obviously we can say that it is a V1 into time, and let's say in the another medium AD is V2 into T. So this TT gets cancelled. This sine I upon sine R, obviously that is a mu2 1. So this mu2 1 is equals to sine I upon sine R is equals to V1 upon V2. So that is the end result that also we have got with the help of your basis of your refraction. In the refraction we had calculated the same formula. So the same thing which we have got over here also, that is a refraction of a plane wavefront at a plane surface. So these are the two results that we have proved. You can see over here also. Yes, so how this exactly occurs over here. So you will get that refracted wavefront. Yeah, and so you can just prove also with the help of that.